Hello and welcome in this third lecture of the Introduction to Artificial Intelligence and Machine Learning for Engineers class. So last time we started to talk about how to solve problems and how problems can be defined in a given tree. The idea of this, of what we saw last time, is that if you have a given problem, it can be rationalized as a collection of possible states, and then you have some possible transition between those states. And as an agent, whoever is going to make those decisions to find the optimal solution, you will start by a given state, which is the initial state of the problem. Then you will have different possible options from there. Those are the different branches, the different actions that you can take. And based on this, based on the action that you choose to take, you will have access to some new states. And in each of those new states, again, you will have access to some new actions. And so in these types of problem, you start with at an initial position, the initial configuration of your problems. And your goal is to find somewhere to find a sequence of actions. For example, to take, in this case, we would have to take first to go on this branch, that would be the first action, and then to go on this branch, that would be the second action, so that you can achieve the goal of the problem. And in this case, the algorithm has found a sequence of action that allows you to transform the initial position of the initial state of your problem into the final state, the goal state of your problem. So these types of tree-based problem, last time we saw for different example of games. For example, like the problem of the fox, the sheep, and the salad, and you have the farmer that wants to move those three items from one side of the river to the next side. In this case, each of the state are defined by the position of each of those three items, and the agent, which is the farmer, has to make some actions, to make some choices based on which items the farmer will take on its boat. And based on this action, every time it takes one item from one side to the river to the other one, then you move from one state to another. So you move within this tree, and the goal in this problem was to go from the initial case where all the fox, the dog, and the fox, the sheep, and the salad are on the left side of the river, and you want to go towards the final goal where all those three items are on the right side of the river. This types of problem is also very general. For example, like if you just want to go from a given initial position to a final position, and if you're just walking and you want to find what is the optimal path to walk from the initial position up to the final position, or to drive, then you have it's the same problem. That's a tree problem, because you have different routes that you can take, and your goal in this case will be to find either the shortest route or the most efficient route that allows you to go from the initial position to the final position. So the main idea in both cases is the same, is that you have a tree which is made of different nodes, which in this case would be the intersection of the streets. And every time you reach a node, every time you reach an intersection, you can make some choices, which is to continue straight, to turn left, or to turn right. And based on the choices that you are making, based on the actions, then you will explore the map, you will explore the tree, and you want to explore this tree in a way that is as efficient as possible in order to find to achieve the final position that you want to reach, which is the goal position. So in this case, the idea is still the same, as you have a tree and you want to explore this tree and to find the most efficient way to go from the initial state up to the goal state. So let's take an example to illustrate this point and see what will be the strategy to solve this. So let's assume that, for example, we start by an initial position there, which is your initial node, and your goal is to find a way to reach the final position, which in this case would be this node G, which is the final position, the goal that you want to reach. And then you cannot go directly from the initial state to the final state, or you cannot go directly from the initial position to the final position. Initially, from the initial position, you have two different routes that allows you to go either to position A or position B, state A or state B. Those two positions are connected, so there is also a route to go from A to B or from B to A. So there is a branch there that is linking those two states with each other. And then from A, you can go to position E or state E. From position E, you will be able to go to state G, the goal. And from position B, you have access to a state C, and then to state D, where state D would be a dead end in this case. So now if we want to build the tree associated to this map. So here you have a map of states that are accessible, that are connected to each other with some different routes. So now if we want to buy the corresponding tree, where on the tree what you illustrate is the possible states that you can access, and the connection, the different choices that you can make. So in this case, if we build a tree corresponding to this problem, so you start with the initial node I, so the initial position. Starting from the initial position, you have two choices, which is to either go towards the position A or to go towards the position B. If you go at the position A, again, you have two choices from there, which in this case would be, starting from A, you can go to position E or to position B again. So there's another way here to go to position B. So you can go to position B or to position E. So those are the two choices, the two different actions that you can take. Starting from state B here, then you have again two choices. You can go to A or you can go to C. Here we will assume that we will never go back to a state that we have already visited. So we never go back to a previous state. So in this case, if you have explored the state I initially, then you don't go back to state I. You always go to states that you have not explored yet. So starting from B, you can go to position A or you can go to position C. Then let's continue to expand this tree. So if you are at the position B here, so in this case, so you were at state I, then you move to state A, then you move to state B. In this case, you have only one choice, because you cannot go back to I, you cannot go back to A. So your only choice in this case is to go to position C, and then from position C you have also only one choice, which is to go to position D, because you cannot go back to position B. Then if you go back to this position E, in this case, you have only one choice, which is to go to position G. And let's finish the tree. So in this case, on this branch here, so you were at position I, you went to position B, then you go to position E. In this case, you have only one choice, which is to go to position E and to position G. And finally, so if you were I, B, A, so I, B, C, then you have only one choice, which is to go to position D, which is the last possible choice. And this is the entire tree of the problem here. Those are all the sequence of action that you can take. There is no other sequence of action that you can take. Again, this is assuming that you can never go back to a previous state. If you have the ability to go back to a previous state, in this case, then potentially you could go an infinite loop where you would go from I, B, A, etc. And you could just do I, B, A, B, A, B, A, and get stuck forever like this. So to avoid getting stuck, we'll just assume that you never go back to a previous state. So here, what we want to achieve with AI is how, starting from the initial position I, what's the most efficient way to go to the position G. So in this case, there's two ways to go to position G. What is the most efficient way? And of course, if you knew already this entire tree, then it's an obvious problem. You can, if you know the entirety of this tree, then it's very easy to go to see that if you use just this path, this is the fastest way to go from position I to position G. The problem is that in real life you don't know the entire tree, because most of the time you only find out about the consequences of your choice after you make those choices. Those the options that you have, you don't know what are the options that you have before making those choices. So in many cases, you are discovering the tree of a given problem as you are making choices. So you are making some choices. Some of them will be good choices. So you will go in the right direction. You will go closer towards the solution of the problem. But sometimes you will do bad choices. And in this case, you will discover that you have reached a dead end, and you will need to go back and make another decision. So in real life, either you or a computer doesn't know the entire tree. So it's discovering the tree. It starts from the initial state I. It makes one decision and will start to discover the tree little by little. And the question is, what is the most efficient way to discover this tree in order to reach the final position, to reach the final goal? And so if you look at, in this case, if you look at this map here, and if your goal is, again, to go from here to here, if you are a human, it's pretty easy. If you just look at it, you will directly realize that there is an obvious way, which is to directly go from there. And in this case, as a human, you have the intuition, but just by looking at this problem, that this is the right way. But for a computer, figuring this thing is actually very complex, because the algorithm will only make decision based on algorithm, based on some condition, and to figure out directly, the computer doesn't have the intuition that human do on what is the easiest way to go from A to G. So in this case, a human would be much better suited than a computer to make this decision much more efficiently. But in real life, when you are facing very complex problem, you have a lot of potential action that you can take. And every time you have you make one action, you open up a whole new range of new possible actions. So in real life, the tree is very large and very deep. Just like when you play chess, every time you make one move, you open up a whole range of new actions, and you cannot process as a human all the possible action that you will be able to make 10 turns from now. Like you cannot predict all the billions of possibilities that you have when you play chess, and you cannot predict so much in advance what the game will look like depending on the action that you can take. And in this case, when you have a very complex tree, in chess, you can only make a finite number of moves. So you have a given tree, and there is only a finite number of possibilities of action that you can take. So this tree has a finite size. There is only a finite number of possible state that you can have in a chess game. And in this case, the computer can potentially become much smarter than you, because it can explore this very large tree that is very difficult for human to comprehend. So in any case, what we need to figure out now is, what are some possible algorithms for computers to explore this tree, to make decisions on which branch to go in order to achieve the final goal of the problem. And one thing to realize here is that as a human, you will try to make smart decisions that look like you are intelligent. But for computers, again, they don't have the same kind of intelligence that humans have. So they have to follow some rules. And so if you just look at the result of what a computer is predicting for a given problem like this, like if you don't know how the computer came up with this option, maybe the computer will look pretty smart and will look like it made an intelligent decision by finding the right route to go from point A to point B, or point I to point G in this case. But the more you know about how the algorithm is working, and the more you know about the main idea of what pushed the algorithm to decide to make this decision instead of another, then you realize that it's only following an algorithm and that it's actually not very smart. So the more you know about the methodology that the computer used in order to find the option, the less smart the computer will look. So, and it's something that is pretty general in artificial intelligence. If you don't understand the reason of why a computer is making certain choices, it looks very smart. But the more you understand about the reason of those choices, the less smart it becomes. And it's not something that is only for computers. It's even for humans or things like this. Like if you look at a chess player and it looks like this player is making moves and you don't understand why, and at the end this person is winning, then this person looks very smart. But if you knew the reasoning that this person is following, and why is it making each action at each turn, then it doesn't look so smart anymore, because it's just following a given algorithm, and just following algorithm is not necessarily a sign of smartness. So this is also something that it's exactly the same in artificial intelligence. Like there is no such thing as smart computers, but computers are just going to follow some instructions, and the more complex those instructions are, the more smart it will become. But as you go through this class, or as you learn more about artificial intelligence, then it can be a little bit deceiving, because you will realize that it's actually not that smart. It's just like algorithms that are predefined in order to reach the final solution in a way that is as efficient as possible. So now let's start to see some possible algorithm on how to find a path that allows you to go from the initial state to the goal of the problem. And for this, we are going to focus today first on uninformed search algorithm. So uninformed search, which means that in this case, the algorithm will try to make some choices when it comes to which action to take. It will try to choose one action or the other, but in this case the computer doesn't know if choosing this action was a good choice or not. In another word, is that if it chooses to go in a given direction, it doesn't know if this direction is getting it closer or further away from the final goal, from the final solution, or the final position. So in this case, it's an uninformed search, in the sense that it doesn't know, every time it makes a decision, it doesn't know if it's reaching closer or if it's getting actually further away from the final goal. Then so this is certain types of problem. When you make a given choice, you don't know if it's going in the right direction or not. So all you know is that every time you are at a given state, you have a given number of possible choices that are offered to you. You will make a given choice. You will either know whether you have reached the goal or not. But if you have not reached the goal, then you don't know if this choice was necessarily good or not, because you don't know if it brought you closer or further away from the solution. So when you are these types of problem, then the only thing you can use is some uninformed search strategy, because the algorithm that doesn't know anything about whether a given action is actually a good or a bad action. So let's take a first example of a search algorithm. And so the first one that we are going to review is called the breadth search algorithm. So the breadth first search. So in this case, just as the name suggests, when you do your exploration, you will favor the breadth of the tree. So let's see what it means. So in this algorithm, so you will first start from the initial position, and now the question is which position do you go to? Which action are you going to take? Are you going to go to position A or to position B? And once you have done this, like, are you what is the route that you are going to follow? And the main idea in the breadth first algorithm is that you are going to systematically explore all the options that you have at each level of the tree. So you are going to systematically explore all the nearest possible solution, and then if none of them are successful, you will go one level more, you will go one step further away. You are going to explore all those configuration, etc. And if none of them are successful, you will go one more step. So in this case, you start with the initial position. So first, you will, by convention, always go left first. So you will try position A. In this case, it's not successful. So you will try position B, not successful. In this case, you have explored the entire first layer, the entire neighbors of the position I. So you will need to go one step further. So in this case, you will now explore this state. That would be the fourth iteration. Then you will explore this state, still not successful. So you will explore this state, not successful. So you will explore this state. Again, you realize that after, in this case, 7 iteration, you still haven't found the goal. So you will go one step further. So you will go to this position C, and you will go one step further. And here at this point, after 9 iteration, you will realize that you have found the goal. So at this point, the algorithm will stop. The search will stop. So in this case, so this is the breadth first search, in the sense that at each iteration, you will systematically explore all the options that you have at each layer. You will explore layer 1. If not successful, you will explore layer 2. If not successful, you will explore layer 3. And like the main advantage of doing this is that at the end, so first you are guaranteed to find the solution. You will find necessarily at some point the goal destination, the goal state that you are trying to reach. And you will also, at the end, based on this, it will give you a solution that corresponds to the shortest path that you can take. For example, in this case, you will never find that there is another way that is to go from the initial position to the final position, which is actually a longer way. You will never find this longer path. You will always find the shortest path. So it's giving you an optimal solution, which is the shortest path, and it gives you necessarily the shortest path because it explores layer 1, then layer 2, then layer 3. So if there is a way by exploring only 3 layers to reach the final destination, then this algorithm will find it. Of course, this algorithm has some drawback. The first thing is that it's pretty slow, and it also requires a lot of memory because you always need to explore all the branches of all the layers, layer by layer. So at the end, if you have a very complex tree with a lot of choices, then you have to keep in memory a lot of possible choices that you have to take because you are exploring all the branches all together. So it ends up potentially with a giant a giant tree that you have to keep in memory, and that can become very inefficient. So we will come back to this to see an example of this problem and how the memory can become an issue. So now let's see another example of algorithm, which in this case is not the breadth first algorithm, it's the depth first search algorithm. So in this case, the way you are exploring this tree is going to be different. So you will still start with the initial state. This doesn't change. Initially, you first have to make a choice, and again, just by convention, you will choose the first the branch on the left as the first condition. In the case here of a breadth first algorithm, then the next choice would be to go to the state B, because this is the state at the first layer, and in this case you want to do an exhaustive search of all the possible state in the first layers before you move to the next layers, because you want to make sure you are not missing a possible state that would correspond to the solution of the problem. In the case of the depth first search, in this case you don't care about exploring systematically all the possible state at a given layer. What you will care is just to go in one direction and testing your luck and see if you were right or wrong. So in this case, starting from A, so step I was the first step, then you go to A. In this case, you will favor the fact of exploring a given route. You will just go in one direction. So you will go to the left again. So you will go to position B, which had the third iteration. In this case, you have only one choice. So you will go to position C, and you will go to position D. At this point in this case here, you will realize that you have reached a dead end. So in this case, you will need to add another element with respect to the breadth first search, which is now we need to have the possibility to back up. So in this case, whenever you reached a dead end, you have made a decision and you realize that, okay, there is no more decision that you can make. So you need to go back. You need to go back to the last decision that you made, the last time you had a choice. And then you will try to make a different decision and see if that helps. So in this case, starting from D, you will go back, you will go back up, you will go back to this just after state A, because this is the last time you had a choice. So in this case, you will go back there, and now you will go to state E. This would be step 5, and from step E, you will go now to state G. And in this case, in 6 iteration, you will have found the optimal solution. You have found the goal, so you have successfully found a way to go from the initial position to the final position. So in this case, the difference is that you always favor to go deep within the tree. So you don't care about potentially having the chance to miss one possible state that was at a layer that you explored. You favor going in one direction and you go as deep as possible, and then if it turns out to be a dead end, then you just back up. So this is when you back up in this case here, and you go back to the last choice that you made, and you start exploring, and again you go deep within the tree. So one advantage of this is that it doesn't require as much memory as the breadth first search algorithm, because you only go in one direction. So you are not systematically exploring all the possible state of each layer. So when you are exploring all those states, if you think of a tree, like the tree, the more you go far away from the center of the tree, the more you have different branches. So the number of branches is growing exponentially as a function of how far you go from the center of the tree. So when you do a breadth first algorithm, then the number of possible states that you have to keep in your memory is increasing exponentially with the layer, the number of the layer. The more you go deep in your tree, the more exponentially you have more and more states that you have to keep in your memory. Here, you don't have to keep all those states in memory because you only go in one direction and you just continue all together in the same direction, and you don't stop until you reach a dead end. So you have less memory, you have less state to keep as a memory. So it's more efficient in terms of memory. But there's some other drawback is that first, you are not necessarily going to find the shortest path. For example, here it's very possible that you could have started in this direction and followed this path, and or you would have realized that, okay, I found the goal, so the algorithm would stop. But it turns out that this would not have been the shortest path in this case, because it will just go in one direction and just continue, and then it will find the goal and it will stop. It will have missed the opportunity to find that there is a shorter path. So these types of algorithm can sometimes be faster than the breadth first algorithm, but it doesn't necessarily give you an optimal solution. It doesn't tell you that the solution was actually the shortest one. And there's another problem, that is that this algorithm potentially may just never find the solution. For example, if you have an infinite route here, if you go from the very beginning, you go in the wrong direction, then you can just continue forever, and potentially you will never find a dead end. You will just continue forever, and you will if you don't find a dead end and if you don't back up, then there is no chance that you will find the goal, because you will just continue and become further away, go further away from the final goal. And if there is nothing that is stopping you, if there is no dead end that is stopping you, then you would never find the goal. So you are, in this case, if you have an infinite tree, you are not guaranteed with the depth first search that you will find the solution. But if you are using the breadth first search, in this case, since you are exploring layer by layer, you know that you will necessarily find the solution. So that's one key difference between those two algorithms. So now let's see how we can represent those two algorithms using a flow chart. So the flow chart is a common way to graphically represent how an algorithm works by highlighting what are the loops that you're making, what are the conditions that you're making, and what are the different instructions that the code is making. So in this case, in the context of an algorithm for a flow chart, so we will put all the instructions as rectangles. Whenever we have a condition, we will write them as a diamond symbol, and whenever the computer has reached, whenever the code has reached an end state, either it has succeeded, either it has failed, we will write this as a circle. So let's see what it looks like. So in this case, so when you start with an algorithm, you always need to initialize, to decide, to come up with some kind of initialization of how you're going to start, like where do you start from. And in this case, what you start from is that you start at the initial position I. And in the case of those search algorithm, the way they work is that you will keep the memory of all the possible states that you find and that you will potentially visit in the future. So those states, they will be, we're going to write them as the frontier. The frontier is the list. It's a list of all the potential states that you have found so far. So those are the potential states that have been found. and those are the states that you are aware of. You don't know what are the other states. You have not found them yet because you don't know the entire tree. If you knew the entire tree, then you would know exactly what is the best way to go from the initial to the final position. But you have only found a certain number of states, and this is your frontier. And so we're going to call this frontier F, and F is a list of the states that you have found. So in this case, the way you're going to start this algorithm is to initialize your initial frontier. So initially, your frontier, the only state that you know is the initial state. So you will this is the only thing that you know. This is your step one. This is the initialization. You say that your frontier is a list of only one member, which is just the initial state I. So then the next thing that you will do is to check after that, is the frontier empty or not. If the frontier is empty, it means that you have no other state that you are aware of. You have explored all the states that you know exist. In this case, if the frontier is empty, then it means that your algorithm has failed. Like you have no other states to visit, so you would not know which state to visit next. So if the frontier is just empty, so if it's empty, there is nothing in your frontier, then if this is the case, then this is a failure. Your algorithm has failed. But if there is still some states in your frontier, then there is more state that you can potentially visit in your tree. So the next thing that you will do is that you will pick a given state. So you will pick a state. We're going to write this state n. So, and you will pick the states from the frontier. So your frontier is a list of states. So you will just pick one from this frontier, and we will see how you pick this state. And this is the state that you are going to visit. So then the next thing is to see, like, the state that you picked, is it the goal or not? If it's the goal, then you have succeeded. You have found the goal. So is n the goal of your problem? Is it the goal? So this is a condition. If this is the goal, then so you have succeeded. The algorithm has found the solution. It has found a way to go from the initial state to the goal. But if not, then you need to continue exploring. So in this case, the next step is that you will, since the state n was not a goal, then you need to find out, like, is there some other choices that have opened up to me now? Is there some possible other state that I can reach from this state n? So in this case, you will need to do what we call expanding the state n. You will need to know from this state n what are all the possible other states that I can reach from state n. So we will illustrate what this means, but you have now to expand the state n. So what you do is that you look at all the other states that are connected to n. Those are called the successors of n, and you are going to add them to f. So you will look at what are all the successors of n, and you will add them to the frontier. So now you have reached a new state. You find what are all the new states that are connected to this state n, and all those new states are potential new states that you have found. So now you are aware of those new states, and so you will add it to the frontier, so that maybe in the future you will explore those states. And now, so you have explore state n. You know that state n is not the goal, so you know that you don't need to go back to state n. So in this case, you will remove this state from the frontier. So you will remove n from the frontier F, because now it's not a state that you have not visited yet. You have visited this state N, you have checked that it's not a goal, so now you remove it from the frontier. You will now start exploring some new states. And after this is where you will loop. So you will go back to this state. You will check is your frontier empty or not. If it's not empty, you will pick another state and you will check if it's the goal or not, and you will do this and you will iterate, and every time you make a decision, you go to another state, you find some new successors, you expand the node N, so you find some new states, you add them to the frontier, and then you keep exploring your tree like this. So in this case, the cost of the algorithm, like the time that it will take to find the goal, is mostly dictated by how many iterations here, how many loops will it take for you to find the goal of the problem, like how many iterations will you have to make. And the memory of this algorithm is mostly the size of the frontier. In the frontier, you keep adding new states. Sometimes you remove states too, but you keep adding new states. So the size of the frontier is what dictates the memory that this algorithm will take. It dictates like how much information, how much states, how much possible state it needs to store during its search. So in this case, both the breadth first search and the depth first search can be described exactly with the same flowchart. The main difference is how you will pick the state that you will explore next from the frontier. That's the only thing that is differentiating those two algorithms. So even though they look very different when you actually see what they are predicting and the kind of states that they are exploring, it's actually like a very similar algorithm in terms of its flow charts. So let's see what the algorithm is doing in practice and what are the states it's exploring and how it's changing the frontier at each step. So let's start with the breadth first algorithm. So breadth first algorithm. So and let's see what this algorithm is doing. So the way we are going to illustrate what this algorithm is doing is to keep track at each step, to keep track of several things, to keep track about the selected node, so the node that is visited by the algorithm, and of how we are going to keep track about how the frontier F is changing. So let's see what the algorithm is doing. So first, initially, you start with the initialization step. So initially, you just say that your frontier is the state I. So that's how you start. So this is step 0. This is just the initialization. All you are doing is to say that initially your frontier is a list of one state, and this is just state I. So starting from this, so then you will move to the first condition. So in this case, the frontier is not empty because it comprises of the state I. So you will go there. You will pick a state N from F. So in this case, there is only one choice, which is to pick the state I. So this is the only choice that you can make. So you will pick state I. That's gonna be the first iteration of the loop. So that's the step number 1. You select the node I, you pick it from the frontier. So then after this, so you move to the next instruction. You check, is the node that you have selected the goal or not. In this case, it is not the goal. I is not the goal. So you have, in this case, you have to add, to detect what are all the possible successors of step I, and you have to add them to the frontier. So in this case, you are now at step I. You need to find all the successors of I. So in this case, you have to expand the node I. So you have to find all the possible routes, all the possible actions that you can take from I. So in this case, you have only two choices. You can turn right or you can turn left. So those are the two routes that you can take. Those are the two states that you can reach starting from I, the two states that are connected to I. So this is what you do when you are expanding the node I. You find all the possible choices that you have, all the possible states that you can reach by doing a transition from I, by doing one action starting from I. And so in this case, so you will expand the frontier. So in this case, so you had a step, you had the state I, and now you will expand it. So you will add the new successors. So you will add so the state A, and you will add the state B, which are the two new states that you have on the two new successors of I. And so in this case, after this, now that you have expanded the frontier, so you will move to the next instruction, which is to remove the state N that you just visited from the frontier. So in this case, since you just visited the state I, so you will remove I from the frontier. So now your frontier is just made of state A and state B. So just state A and state B. State I has been removed. Okay, so now starting from this point, so you will go back here. You will check that no, the frontier is not empty. I have two states in the frontier, so I will pick one state. So in this case, in the case of the breadth first, you will always pick the node, the state that you added first. You will always you will pick the oldest state that you have in your frontier. So in this case, you pick the oldest state. At each iteration, you will go back to the oldest state that you have not visited yet. So in this case, so in your frontier, you have two elements, A and B. So in this case, the oldest in this case would be element B. So now you are going at step 2 to go to step A. So you have two states, state A and state B. The oldest one that you added to the frontier was state A. So now you will visit state A. So you will visit state A. A is not the goal, so you will need to add the successors of A. So now you have explored A, so you will need to add the successors of A. You have two successors. You expand the node A, you have two successors, which is B and E. So now you add them to your frontier. So in your frontier, you used to have A, B. So now you need to add the two new successors, which is now B again, but this time it's this B here, which is not the same as this B. It's the same position, but you found it in a different way by taking a different route. So you add this one to the frontier, and you add the other state, which is the state E. You also add it to your frontier. Then you remove the last state that you just visited, which was state A. You have visited this state, so now you remove it. And now, same thing, so you will pick as the next state to visit, you will pick one state from the frontier, and again, you will pick the oldest state. In this case, the oldest state that you still haven't visited is this state B here, which corresponds to this state B. This is the oldest state that you added and that you still have not visited. So this is the next one that you are going to visit. So now you will go to state B. That's going to be the third iteration. So B is still not the goal, so you will need to expand this node, and in this case, when you expand, you have two possible successors, which is state A and state C. So you will need to expand the frontier. So initially you had B, you had another B, you had E. Now you will need to add the two new successors, A and C, that you just found. You remove B because you just visited it. Now you select the next state to pick, and in this case you select the oldest state, which in this case is B, which is this B. This is the oldest state that you added to your frontier that you still have not visited. So now you go to B. This is the fourth iteration of the algorithm. B is still not the goal, so you will need to expand state B to find all its successors, and you add them to the frontier. So now in the frontier you have B, you have E, you have A, you have C, and now you add another C. You remove state B that you just visited, and now you go back to the oldest state that you still have not visited, which is E. So E becomes the next state. That's iteration number 5. You expand state E, you find that there is a state G here. You add it to the frontier. So now you have E, you have state A, you have state C, you have the other state C. You just add the new state that you just found. You remove state E because you just visited it. You go to the next state, which is the oldest that you have not visited yet, which is state A. You expand A, you find E, you add it to the frontier, to the list of your frontiers. So let's do that. So you have A, C, C, G. Now you add the new one, which is state E. So same thing. You just remove A because you just visited it. You go back to the oldest state, which you have not explored yet, which is state Z. You expand it, you find state D. So now you are at step 7. You have just explored state C. So you see state C, but you are going to remove this one because you just visited it. So you have C, G, E, and the new state that you just found is D. Next, you are going to go to the oldest that you have not visited yet, which is C. So same thing. So now you go to C. That's step number 8. You have C, but you are removing it. You just visited it. Next one is G, E, D, and here there is nothing to expand. Like actually, there is something to expand. You just found a new state D, so you are going to add it to your frontier. So you add this D, okay. And now, so you go back to the next step that you still haven't visited it, which in this case would be this step G. So now this is iteration number 9. You are visiting state G. Here, it turns out that state G is the goal. So this is where your algorithm will stop. Now you found the goal. So you found a way to go from the initial state to the final state, and you have done this by exploring layer by layer, layer 1, then layer 2, then layer 3, and you have found, by doing this strategy, you have necessarily found the shortest path to go from state I to state G. But as you can see here, it took you quite a few iterations, like it took you 9 iterations to find this state. So it actually took you a lot of time to find this state. And you had to store a lot of information. You end up with some big frontier, some big list of states that you have to keep in memory just in case you don't find the goal, you have to keep the memory of all those other possible states that you need to keep in memory just in case, as a future option. If you haven't found the goal, you need to explore the next state, and you need to keep the memory of a lot of possible states. And the size of this frontier can increase exponentially if you go deeper and deeper in the tree. You have more and more options that becomes open to you, so the size of this frontier can become very high. So you can have a memory issue here, because you cannot keep on the computer, you have a finite memory, so you cannot keep the memory of everything. At some point you will run out of memory. So now let's see how the depth first algorithm is working. So now we're going to focus on the depth first algorithm. So same thing, the flowchart is exactly the same. The only thing that is going to change is how you pick the state to explore from the frontier F. We're going to keep exactly the same tree as an example, and same thing, we're going to explain how this algorithm is working by keeping track of the step that is visited at each iteration of the algorithm. So for each step, we are going to keep track of the selected node, the node that is visited, and we are going to keep track of what's in the frontier. So like what is stored in the frontier F at each iteration of this algorithm. So let's do that. So same thing. So we start initially by saying that the frontier at step 0, the frontier is just the position, the state I. So this is the same beginning as the previous algorithm. So we are at this position here. So we initialize the algorithm by saying that the frontier is just the state I. The frontier is not empty, so we will need to pick a state from the frontier. So in this case, we are going to say that we are going to pick state I. This is the only state that we have in the frontier. So this is going to be at the next iteration. So we are going to pick state I. We have only one choice in this case. So this is not the goal. State I is not the goal. So we have not reached a success. We need to determine all the successors from the state I and add it to the frontier. So far it's the same thing as the breadth first algorithm. We need to say that we are going to add the new successors. The successors of state I is state A and B, and we are going to add them to the frontier. Here the difference is that in the state first, we are going to add them at the beginning of the frontier, not at the end. We are going to add them at the beginning of the list. So let's see what this changes. So now we are going to add the two new successors, which is A and B. So those are the two new successors, the two new states that we found. We used to have state I in the frontier, but we just visited it, so we are going to remove it according to this instruction, and now we go back here. So the frontier is not empty, so we are going to again pick a state of the frontier, but this time the main difference between the depth first and the breadth first is that in the breadth first, you are always picking the oldest state that you added to your frontier. In this case, you are going to pick the newest state that has been added. So you are going to pick the one of the latest state that you just added. You are not going to pick the oldest state like in the breadth first algorithm. So in this case, you are going to pick the first state of the list. So you're going to pick A, for example, because we said that the algorithm is always choosing to go left in this case. So at iteration number 2, you will go to step A. So A is not the goal, so you will need to expand the node A. So same thing, you have two nodes that are accessible from the state A, so you will add them to the frontier, but same thing, you will now add them at the beginning of the frontier. So you will add the two new states B and E, the two new states that you just found by expanding state I. You will add them to the beginning of the frontiers. Then, so in the frontier, you still had A and B, so this was the frontier at the previous steps, but now you just visited A, so you can remove it. So, and now using based on the depth first, the next state that you are going to follow is again the newest state that you just added, which in this case is at the beginning of the list. So now you will go explore state B. So you will at iteration number 3, you go to the state B. So you will expand it. So you will add C as a new state that you add to your frontier. You add it at the beginning of your frontier. So then you had the rest of the frontier, which is B, E, and B. You remove B because you just visited it. And then you pick again the newest possible state, which in this case is C, the first element of your list. So next you will visit step C. So you will now reach here. C is still not the goal, so you will need to expand it, add it to your frontier. So now the state that you have is, so the new state D that you just found, you add it to the first position of your frontier, and the other one that you have was state C, state E, and state B, but you remove state C because you just visited it. The next state, you choose the newest one, which is state D. So now you are going to move to state D. This is the fifth iteration, you are at state D. In this case, at state D, there is no new successors. When you expand state D, there is no, you don't find any other state that are accessible from state D. So at this point, this is when you will need to back up, and the way you back up in practice, there is no need to add any special instruction for this. The way you back up in practice is that since there is no successors, then your frontier remain unchanged. So you have state D, state E, and state B, but you just visited state D, so you are going to remove it. So now you will still go to the newest state from the frontier that you have not visited, which in this case turns out to be state E. So it's still exactly the same algorithm, and just by visiting the newest state of the frontier, this is how in practice you will do this this backing up without changing the algorithm itself, just by changing the way you pick the states from the frontier. So now you reach step 6. The state that you are visiting is now state E. So you need to expand state E. So you find a new state G, you add it to the list of your frontier. So the state G is the new state. Then you still have the old state E and B, but you will remove state E because you just visited it. The next state that you will visit is the newest one, the first element of your list. So now you will go to state G. So this is the 7th iteration. You go to state G, and here you realize that state G was your goal. So this is where the algorithm stops, and this is where you find a route that allows you to go from the initial position to the final position. So in this case, what we can say is that in this case, we found the solution a little bit faster than with the breadth first algorithm, but this is just by chance in this case. So we found with only 7 iteration. But the main difference is that in this case, the frontiers never become so big, because you never need to keep the memory of so many possible trees at each layers. So these types of algorithm relies on a lower memory than the breadth first algorithm. But again, it's possible that if this tree was actually infinite, then if this branch was infinite, the algorithm potentially could have continued forever on this branch and would have never found the goal in this case. So this depth first algorithm is not guaranteed to find the goal of the problem, assuming that the tree is infinite. If the tree is infinite, then it's possible that it can miss the goal by not systematically exploring all the possible states that you have at each layer of the tree. So now to finish, let's review the criterion that we can use to evaluate search strategies. So what are the criterions of evaluation? So what makes a search algorithm a good versus a bad search algorithm? What are the pros and cons of each search algorithm? So there is 4 main characteristics that discriminate what we will refer as a good or bad search algorithm. The first condition, which is usually pretty important, is the completeness. So completeness. This is the first condition that is pretty important for a search algorithm. And the completeness of a search algorithm is if there is a solution that exists to the problem, is the algorithm guaranteed to find this solution? If the solution exists, will the algorithm necessarily find it? Will it necessarily be found by the algorithm? So this is not guaranteed. Certain algorithm will necessarily find the solution if it exists, but they can be very slow in return. But some algorithm will be very fast, but it's possible they will miss the solution. So there's usually a balance here between efficiency and the completeness. The second criterion is the optimality. So the optimality is the optimality of a search algorithm is if it finds the solution, is it guaranteed that it's the optimal one or not? Will it find, in this case, the shortest path to go from the initial position to the final position? Or will it just maybe find a solution, but this solution is not guaranteed to be the shortest possible path? So will it find, will the algorithm find the optimal solution of the problem? So it's possible that it will find a way to solve this problem, which is actually not the optimal solution. So this is about the optimality. Does it find the shortest path, the optimal solution, or does it just find one solution and we don't know if it's an optimal solution or not? The third thing is the time complexity. The time complexity is assuming that the algorithm finds a solution, how long will it take to find this solution? So how long will it take? Like how much time? How long will it take? So in this case, if you think about algorithm, it's the way you measure this is how much CPU time, how much time how much time the processor is going to be working to solve this problem. Like how much computing time does it take to solve this problem? And the last thing is about the space complexity. The space complexity is slightly different from the time complexity. In the time complexity, you just think about, okay, how many iteration do I need to solve this problem? How many operations on my computer do I need to solve this problem? The space complexity is how much possible states have you explored in the tree. Ideally, you don't want to explore this tree, you just want to go directly towards the most optimal solution. But if the algorithm is not very efficient, then it will explore a large fraction of the tree before it finds the optimal state, the goal that you want, the state goal that you want to achieve. So in this case is how many states have been explored? How many states have been explored? Like, what is the number? What's the fraction of the space, the fraction of the tree that has been explored before you find the goal of the tree? So in this case, the way you measure it is what is the size of the frontier. If the frontier become very large, it means that you have a lot of states that you are exploring or planning to explore, which means that in this case it will take a lot of memory. So in this case, the space complexity characterize how much memory this algorithm will require in order to find a solution. And this is an issue because if you want to find a solution that takes a very, very large number of states in order to find the goal state, then potentially the memory will become very large. And if the size of the frontier starts to exceed the memory of your computer, then the computer will just crash and the algorithm will stop because it has run out of memory. It cannot keep track of all those states that needs to be explored, and the search will fail. So let's just summarize like for the two algorithms that we saw, which is the breadth first algorithm and the depth first algorithm. So in this case, if you think about those two algorithms, let's see what are their strength and weakness based on those criterions. So based on those 4 criterions, so we say the first case, is it complete or not? What is the completeness of the algorithm? In this case, if you think about the breadth first, the breadth first search is guaranteed to find the solution, assuming that you let this algorithm run for a long time. So there is no way, since this algorithm is systematically exploring all the possible states that are accessible layer by layer, it's guaranteed that it's going to find the goal state if it exists. So in this case, this algorithm is complete. In the case of the depth first, again, it's not guaranteed to find the goal of the problem, because it can just go follow one branch and continue forever along this branch. And if this branch turns out to be an infinite route, they will just follow this route and will go further and further away from the goal, and will completely miss the goal and potentially will never go back. So if the tree is infinite, then the depth first search algorithm is not complete and can finish and can eventually run out of memory or run out of CPU time without finding the optimal solution, without finding the goal of the problem. So then we move to the second criterion, is it optimal? So if it finds the solution, is it guaranteed to be the most optimal solution? So in the case of the breadth first, it does find the most optimal solution all the time, because again, it explores layered by layered. Layer 1, if it's not on layer 1, it goes to layer 2. If it's not on layer 2, it goes to layer 3. So it's guaranteed by systematically exploring all the states at each layer, it will necessarily find the goal at with the minimum number of layers needed to find this goal, which is different from the depth first, which in this case you would just follow one route and then back up if you chose the wrong route. So it can find the goal, but it's not guaranteed that it will find the shortest way, the minimum number of actions to achieve this goal. So the next return is about time. It's how much time does it take. And in this case, both the breadth first and the depth first, they are both pretty slow algorithm, because in this case, those are two uninformed algorithms. So they don't know if they are taking one step in one direction. They don't know if they are making the right move, if they are getting closer to the solution or not. But usually the depth first is still faster than the breadth first, because the depth is going to go in one direction, is going to try its luck, and it's possible it can find the solution very fast if it got lucky. The breadth first is typically very slow because it tries systematically all the possible states layer by layer, so this takes more time. But both of those algorithms are typically pretty slow. And then the last thing is the space complexity. So in this case, the breadth first the breadth first algorithm has a lot of advantage. It's complete, it's optimal, but it has some drawback. It's very slow, and the other drawback is that it requires a high memory. So in this case, you need a high memory in order to explore the tree. So that's one drawback of this algorithm, is that it will always require high memory, and this comes from the fact that the frontier becomes exponentially larger as you go from one layer to the next to the next. The size of the frontier becomes larger and larger. If you think of the depth first, it requires a lower amount of memory, because it doesn't need to keep track of all the states of each layer. It just needs to keep track of one path, which is the path that it has chosen to follow, and it just needs to remember this path so that it can back up and go back to the last choice that it made if it turns out that it has reached a dead end. But in this case, the number of states that it has to keep in memory does not increase exponentially with the depth of the tree. It just it increases just linearly with the number of layers that it visits. In this case, if you have layer 1, layer 2, layer 3, and let's assume that each layer you have 2 choices, then in the case of the breadth first, at layer 1 you have 2 choices, then at layer 2 you have 2 by 2, which is 4, then at the next layer we'll have 4 by 2, which is 8, then 16, then 32, then 64. So in this case, the number of states that you have to keep in your memory increase exponentially with the number of layers. But in the case of the depth first algorithm, you only go in one route, so you just need to keep in memory the states that you are visiting in this route. So every time you go to the next layer, you will need to keep in memory one more state. So every time you go to the next layer, you need to keep just one state as a memory. So in this case, you will need to keep the memory of 1, 2, 3, 4, 5 instead of 2, 4, 8, 16, 32, etc. So you, in this case, the number of states that you have to keep in the memory of the frontier just increase linearly as opposed to exponentially with the breadth first. So the depth first is in that sense a more efficient algorithm, because it requires a lower amount of memory than the breadth first algorithm to find the solution. So in this case, there is not necessarily some right or wrong answers when it comes to choosing a given algorithm to explore a given problem or to find a given path in a given tree, to find the best route to go from point A to point B. It mostly depends about what are your criterions. Do you care about finding the optimal solution, like the shortest path? Then in this case, you will favor the breadth first algorithm, and maybe in this case you will not care that it's very slow and that it takes a lot of memory. But on the other hand, if you want to find, if memory becomes an issue because like the tree is very large, then necessarily you will need to favor the depth first algorithm because it requires a lower amount of memory. It is better suited for very large trees that potentially otherwise could not be solved by breadth first algorithm because the memory that would be required would be just too large. So there is some better algorithm than the breadth first and the depth first. An improved class of algorithm are the informed algorithm, which are some algorithms that are aware every time they make one choice, they are aware whether this choice is actually bringing them in the right direction, bringing them closer to the goal or not. And those types of algorithms are not always possible to implement because sometimes you make one choice, you go to one state and you don't know if this was a good choice or not. You don't know if you are getting closer to the goal or not. But if you know this information, then it's going to be more efficient to adopt informed algorithm, which is what we are going to see in the next lecture.